In this video, we're going to see an important difference when we're doing the halogenation reactions in the presence of a solvent that could also act as a nucleophile. So our first step is going to look very much the same as the reaction we saw in the previous video. So we're going to have this pi bond come and attack. We're going to have the bond between the two bromines break, and also at the same time, the bromine is going to go and attack back. This is going to give us our bromonium ring. And in this case, I'm going to show it on the top of the molecule again, but you could also have shown this going back into the page on both of these bonds. That bromine is going to be positive. What's going to happen to this CH3 group here is if the bromine and that ring, that three-membered ring, is forming on the top of the molecule, this CH3 group is going to be pushed to the back. And so we're going to show that CH3 group as a hash because that's going to get pushed towards the back. Now we're also going to have our Br minus left behind. But this is where we always have to have a decision point once we get to this point. We're asking ourselves, we're looking back at that original reaction. Do we have a nucleophile in the solution or not? Is this Br minus the only thing we have that can do the attack? We don't only have this in this case. We also have water. And when water is written under the arrow like that, that means that it's actually being used as a solvent in the reaction. What that ends up meaning is that there's a lot more water molecules than there will be of this Br minus molecule. So the water's molecules are going to be surrounding this intermediate, especially because now it has a positive charge. It's going to be surrounding that intermediate, trying to stabilize it. That's what solvents try to do. And so the water is going to be right there. It's going to be able to go and attack and open up this intermediate. Next thing we have to ask ourselves, so we already considered that stereochemistry. When it attacks, we also have to consider the stereochemistry. So what direction is it going to attack from? Because that's going to mean how is that oxygen then going to be attached to the molecule? And also we have to ask where the attack is going to occur because we have both of those positions, and this is going to be the same rationale as with our other, with our oxymercuration. We want to attack at the more substituted carbon because it is able to hold that delta plus. So this bromine right now being positive doesn't really like to be positive. It's going to be pulling on both of those carbons, and it's actually going to be able to pull away from this carbon more at the top because it's more substituted. So the carbon at the top has that CH3 group and this carbon to help it out. Whereas the carbon down here would only have that carbon in the ring and maybe that top one to help it out that charge. And so we don't have that extra CH3 group that we have up here. And so that delta plus is a lot more stable on that carbon, and that's where the attack is going to occur. So we've decided where the attack is going to occur. We've decided what is going to attack, which is the water. That's actually the first thing we decided, that the water was going to attack because we saw that in our reaction up here. So we're like, okay, this water is going to attack, and we're like, okay, it's going to attack this position because that's more substituted. And then when we're going to draw the attack, we have to decide how is it going to be attached. So we can go ahead and just attack right in there, and then we have to move that bond onto the bromine. Now we come to another decision point. At the bottom of the ring, that bromine is still coming out of the page because we didn't touch that bond. So that's still attached like that. But what's going to happen when the water comes to attack, just like we saw in our previous example when the Br minus came to attack, we have to come from the opposite side. So the bond is going out of the page. We need to come from behind the page in order to break that bond, because that's where that antibonding orbital is. That major part of that antibonding orbital is right there. That's where we need to put the electrons in to break this bond. And so that's going to make this water attached to the back of the molecule. So let's go ahead and draw that in. So that's how the water is going to be attached. Still going to have its two hydrogens, so it's going to be positively charged. What that means for that CH3 group, the CH3 group is constantly being pushed around in this reaction. Originally, it was just kind of pushed back. Now, because of this attack, it's actually going to invert and be pushed forward. So we're going to actually have this CH3 group now coming out of the page because the water attacked from the back. And so during that process of the attack, the CH3 then gets pushed completely to the front of the page. And then we just have a few more steps to draw. We have that water attached with its two hydrogens, so we do want to make sure that we're deprotonating to get a nice neutral product. And that's going to give us our product here with the OH group and the bromine added to the molecule in an anti fashion. So these are both added anti to one another, and the CH3 group is just kind of getting pushed around based on, what's happening within the reaction. But the OH and the Br are the important ones to say what their arrangement is. So we have the bromine ending up on that less substituted carbon in one direction, and then the OH, because that was the nucleophile, coming in and ending up on the more substituted carbon.